The 1961 timetable revision by Japanese National Railways known as Sunroku (TO) marked the nationwide deployment of limited express services operated by diesel railcars, extending modernization benefits even to the underdeveloped lines in Hokkaido. At the time, traveling from the Kanto region to Hokkaido typically meant using JNR, with a transport network formed by limited express services running through the Tohoku Main Line, the Seikan Ferry route, and onward from Hakodate to Sapporo and eastern Hokkaido. However, subsequent changes in transportation trends and the worsening financial condition of JNR had a severe impact on railways in Hokkaido. In response, speed upgrades and electrification were rapidly pursued in Honshu and Kyushu, while regions with lower transport volumes, such as Hokkaido and Shikoku, were left behind. Although some sections in Hokkaido were electrified with AC systems during the 1960s, the coverage was limited to short segments, and most services continued to be operated by diesel railcars. In Honshu, 181 series DMUs began operating at 120 km, but no Hokkaido-specific version of the 181 series was introduced, and the aging 80 series DMUs remained in use. As a result, the maximum speed was capped at 100 km/h, and even on lines with favorable alignment and robust track structures, high-speed operation remained unattainable for an extended period. With the rapid construction of Shinkansen lines proving unrealistic, JNR sought to overcome its financial crisis by developing tilting EMUs and tilting turbine-powered railcars for conventional lines. While the tilting EMUs entered mass production as the 381 series, the tilting turbine-powered railcars were left in limbo due to the failure of gas turbine propulsion. In Hokkaido, where further electrification was out of reach, there were few viable options. Meanwhile, the aging 80 series DMUs were increasingly problematic in terms of passenger comfort and maintenance, raising expectations for a new generation of railcars. It was in this context that the 183 series DMUs were introduced. Unlike the 181 series, they were not designed for demanding operations. While equipped with the latest passenger amenities of the time, their running performance was compromised. Prioritizing reduced maintenance burden, both output and maximum speed were lowered, and the railcars were developed to match the speed of the 80 series limited express services while minimizing operating costs. This strategy proved successful at the time, earning praise from passengers and operators alike, especially when combined with excellent cold and snow resistance features. Thus, the 80 series limited express services were gradually replaced by the 183 series, offering more comfortable travel. However, an unexpected shift in the era soon struck. Public criticism of JNR's mounting deficits intensified, prompting the government to move toward privatization. If the company were to be split regionally, the consequences would be dire. For regional bureaus like Hokkaido and Shikoku, which lacked Shinkansen lines or other high-revenue routes, such a move would be tantamount to a death sentence. To overcome this difficult situation, it was deemed essential to thoroughly streamline operations and accelerate services to attract more passengers. As a result, efforts to reform the internal structure of Japanese national railways gained momentum nationwide. At the time, Hokkaido's expressway network was limited to short segments around Sapporo and posed no immediate threat to JNR. However, improvements to the general road network were rapidly drawing passengers away from rail services. The most advanced diesel railcars available were the 183 series, which had been introduced with performance compromises equivalent to the 80 series limited express. Therefore, time savings through high-speed operation could not be expected. To achieve higher speeds, not only track upgrades but also high-performance rolling stock were required. Various simulations were conducted to assess feasibility, and research began on potential solutions. The first proposal was to develop diesel railcars with high-speed capabilities equivalent to the 181 series. This would allow operation at 120 km/h, which could yield significant benefits on Hokkaido's main lines with favorable alignment. However, to consistently deliver output comparable to the 181 series, engine improvements were necessary. At the time, although the 181 series operated with reduced output, it was still rated at a maximum of 550 horsepower and a continuous rating of 470 horsepower. Efforts were underway to develop lighter and more efficient direct injection engines, but they would not be ready in time. The next option was to revisit the gas turbine-powered railcars, which had previously failed with the Kiha 391 series. Gas turbines offered the advantage of enabling ultra-lightweight vehicles, which could reduce the cost of track reinforcement. However, the technical hurdles were even higher than those for direct injection engine development. Some proposals suggested adopting electric transmission to limit the introduction of new technologies. Yet even with electric transmission, weight reduction could only reach the level of conventional DC EMUs. Operating at 120 km would still require substantial track upgrades. The remaining option was electrification. Technically, this was the most realistic approach. The 381 series EMUs were already in mass production, and developing an AC version would be relatively straightforward. Although the issue of heavy transformers remained, the required track reinforcement would be less than that for diesel vehicles. However, the greatest obstacle was the investment in ground facilities for electrification. It was ultimately rejected as financially unviable. By the time privatization approached, it was assumed that next-generation diesel railcars would eventually be developed. In the meantime, efforts were made to continue operations using the existing 183 series. To explore the potential for speed enhancement with the 183 series, tests were conducted on the Sekisho line, which had track structures originally designed to support 120 km operation. By modifying the gear reduction ratio, the 183 series could technically reach 120 km. However, the required modifications were extensive, and acceleration performance dropped by 20%. This led to significant speed reductions even on gentle gradients, effectively cancelling out the benefits of higher speeds on flat and straight sections. An alternative proposal was to replace the wheels before they became excessively worn. With new wheels of 8 60 mm diameter, the engine operating at its regular maximum output of 510 horsepower at 2000 rpm could achieve a speed of 1/16 km. While 120 km operation was still out of reach, 110 km was comfortably attainable. However, when the wheels wore down to 820 mm, 110 km became the upper limit. Normally wheels would be replaced when worn to 780 mm, but by changing them earlier at 820 mm, 110 km operation could be maintained. This method required no vehicle side modifications other than brake reinforcement, minimized additional investment, and was considered the most straightforward solution. However, it doubled the wheel replacement frequency, resulting in increased maintenance costs. The next option considered was operating the engine at higher RPM. To achieve 110 km with wheels worn to their minimum diameter, the engine would need to run at 2100 rpm. While increasing RPM by just 100 might seem simple, it wasn't. Diesel engines produce output nearly proportional to RPM, which directly increases fuel consumption and heat generation. The engine was designed to operate at a regular maximum of 510 horsepower at 2000 rpm. Exceeding this and continuing fuel injection could lead to overheating and even mechanical failure. Moreover, the torsional vibration resonance point of the engine's rotating system occurred precisely at speeds between 100 and 110 km/h. Operating continuously at this speed with standard fuel injection risked shortening the crankshaft's lifespan. To address this, fuel injection was reduced above 2000 rpm, lowering output to reduce heat and vibration. This allowed the engine to safely reach 2100 rpm without modifications to the engine or cooling system, keeping retrofit costs low. Although acceleration performance above 100 km declined, performance below that threshold remained unaffected, avoiding the overall performance degradation seen with gear ratio changes. Once the train exceeds 100 km, the driver can simply notch down slightly. However, even at the same operating speed, variations in wheel tread wear between individual vehicles result in differences in engine RPM. To compensate for these discrepancies, a governor mechanism was incorporated to automatically reduce fuel injection when the engine speed exceeds 2000 rpm. This allowed for consistent traction control across the fleet, eliminating the need for drivers to manually adjust for vehicle-specific characteristics. This approach proved more cost-effective than early wheel replacement, and Sekisho line required no track upgrades. A 110 km/h trial run was conducted on the Sekisho line, and with no major issues, commercial operation at that speed began. Thus, for the first time in years, high-speed rail operation in Hokkaido was seriously discussed, and though the effect was modest, realized, largely driven by the looming pressure of privatization,